Alright folks, welcome back. We have reached the 7th and final section of Unit 4 of AP Calculus using LHospitals Rule for determining limits of indeterminate forms. And we talked back in Unit 1 about indeterminate forms when we were finding limits. We talked about the indeterminate form 0 over 0. When we're talking about LHospitals Rule here, we're going to talk about the forms 0 over 0 or infinity over infinity are two places where we might be able to use or where we can use usually LHospitals Rule in order to find the limit, if the limit exists. There are other indeterminate forms that we're not going to cover in this course, but there are some other indeterminate forms that we can use LHospitals Rule on. Maybe I should do some extension videos on those forms at some point in time, but I'm going to wait until I have the bare bones of the course laid out. So for now, we're just going to focus on 0 over 0 and infinity over infinity. You see the basic statement of LHospitals Rule here. Suppose that f and g are differentiable functions on an open interval I containing a, and that g prime of x does not equal 0 on the interval if x does not equal a. If the limit as x approaches a of f of x over g of x produces one of the indeterminate forms, 0 over 0 or infinity over infinity, note that the infinities here can be either positive or negative, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So basically what this tells us is that if I'm taking the limit as x approaches a of some rational function or some fractional function where both f of x and g of x approach 0 or approach an infinite value, okay? They both approach 0 or they both approach an infinite value. Not one approaches 0 and the other approaches an infinite value. They both have to approach 0 or they both have to approach an infinite value. Then I can find the limit by taking the limit approaching the same value and taking the derivative of the numerator and the derivative of the denominator. And guess what? If they end up as 0 over 0 or an infinite value over an infinite value again, I can apply LHospitals Rule again. And I can continue doing that until I get something that is not of that form. So let's take a look at this. We'll look at a bunch of examples here. Example 1, find the limit as x approaches 0 of sine of x over x. First of all, I try to substitute 0 in here, and I see that this is indeed the indeterminate form 0 over 0. So I'm going to now apply LHospitals Rule, and this will be equal to the limit as x goes to 0 of the derivative of sine of x over the derivative of x, which is 1. And now this is a limit that I can find using substitution. I substitute 0 in, the cosine of 0 is 1, and so this is 1 over 1, and this limit is just 1. But you should have already known that as soon as you saw that limit there. I'm going to change colors. I don't really like this color very much. All right, let's go on to example 2. Find the limit as x approaches 0 of e to the 2x minus 1 all over x. Again, we see that the denominator is 0. If we substitute 0 into the numerator, we've got e to the 0, which is 1 minus 1. So again, this does indeed lead to the indeterminate form. Determinate form 0 over 0. So I'm going to use LHospitals Rule. And this is going to be equal to the limit as x goes to 0. And now I'm just going to take the derivative of the numerator. The derivative of e to the 2x minus 1 is 2e to the 2x. And the derivative of the denominator is 1. And then I'm going to find this limit via substitution. And it becomes 2e to the 0 over 1, which is just 2 over 1, or 2. And so our limit to in example 2 is just 2. All right, let's go ahead and do example 3. Again, we try to substitute. We've got 0 minus 0 over 0, which is, again, the indeterminate form. 0 over 0. So I'm going to apply LHospitals Rule. This is going to be equal to the limit as x approaches 0 of, and I take the derivative of the numerator. That becomes 3 minus cosine of x. And the derivative of the denominator is 1. And then I can go ahead and, well, wait a second. Whoop. Just erase. And now I can go ahead and take this limit via substitution. I just saw myself do that up there. And this becomes 3 minus the cosine of 0 over 1, which is 3 minus 1 over 1, which is 2 over 1, or 2. You probably don't need to go through that much detail in the arithmetic there. By the way, you'll notice in all of these, I knew after applying LHospitals Rule one time that I wasn't going to have to apply it again, because in every one of these cases, the denominator was 1 after I took the derivative that one time. This will not always be the case. In fact, let's see what happens here in example 4. Find the limit as x approaches infinity of x minus 2x squared all over 3x squared plus 5x. If we imagine what happens as x approaches infinity, the numerator here approaches a negative infinity because the largest power, x squared, is negative. And the denominator approaches a positive infinity. And so this is, again, an indeterminate form. We've got an infinity over infinity situation here. So we're going to apply LHospitals Rule. This is going to be equal to the limit as x goes to infinity. And now I'm going to go ahead and take my derivative of my numerator. Derivative of the numerator is 1 minus 4x. The derivative of the denominator is 6x plus 5. I evaluate this again, and again, I have the indeterminate form, negative infinity over infinity. So I'm going to apply LHospitals Rule again, and this is equal to the limit as x goes to infinity of negative 4 over 6. And so our limit here is going to be negative 2/3. And that should jive with what you learned earlier in how to find, limit as x approaches infinity of a rational function like this using some other techniques. Those other techniques, however, would have been useless on an example like example 5. When we look at this, the limit as x goes to infinity of natural log of x over x. This is, again, an infinity over infinity indeterminate form. And so I'm going to apply LHospitals Rule. This becomes the limit as x goes to infinity, and I take the derivative of the numerator, that's 1 over x, and the derivative of the denominator, that's 1. By the way, when we're applying LHospitals Rule like this, we can simplify this result, and so I'm just going to change this into the limit as x goes to infinity of 1 over x, and if we imagine as x gets bigger and bigger, 1 over x approaches 0, and so that is my limit here of the natural log of x over x as x goes to infinity. Okay, let's keep going. Example 6. Find the limit as x goes to 3 of x squared minus 9 over x squared plus 2x plus 8. Don't fall into the trap. Don't just start taking the derivative. Now that we know LHospitals Rule, don't just start taking the derivative of the numerator and denominator every time you try and find a limit, because in this one, if I substitute 3 into the numerator, I get 0, but if I substitute 3 into the denominator, I get 9 plus 6 plus 8, I get 23. And so this limit is actually equal to 0 over 23, or 0. Okay, make sure limit is an indeterminate form. Determinate form before trying to apply LHospital. All right, example 7. Find the derivative with respect to x of the quantity sine of 2x over x. Hey, guess what? We're not even finding a limit here. And just because we now have this LHospitals Rule that we can use to find limits, it doesn't change the way we take derivatives of rational functions like this one. We'll just take the derivative as we did before using the quotient rule. Low times the derivative of high minus high times the derivative of low. Square the bottom, and away I go, and I end up with this as my derivative. Okay? Quotient rule hasn't changed. Just because we've learned how to use LHospitals rule to find limits. All right, keep plugging. Example 8. I'm going to try and get through all of these in one lesson. If I substitute 0 in here, I get 1 minus 1 minus 0. That's 0. This is a 0 over 0 indeterminate form. So I'm going to take the derivative of the numerator and the derivative of the denominator here. The derivative of the numerator here is 1 over 2 square root of 1 plus x minus 1/2 all over 2x. Guess what? This is 0 over 0 again. It's still an indeterminate form, so we're going to take the derivative again of the numerator and denominator. I'm going to do the denominator first. Derivative of 2x is the easiest. Derivative of 1/2 times the square root of 1 plus x. This is 1/2 times 1 plus x to the negative 1/2. So it's going to be negative 1/4 times 1 plus x to the negative 3/2. And the derivative of 1/2 is 0. And now I substitute in, I get negative 1/4 times 1 all over 2. And my limit is negative 1/8. All right. Example 9. Substitute 0 in, boom, it's 0 over 0. I apply LHospitals rule. It's the limit as x goes to 0 of 1 minus cosine of x over 3x squared. Guess what? Cosine of 0 is 1, so this is 0 over 0 again. So I apply LHospitals rule again. Take the derivative of the numerator, and that becomes sine of x. Derivative of the denominator is 6x. And I substitute again, and I see that it's 0 over 0 again. And so I apply LHospitals rule one more time. And we end up with cosine of x over 6, which we can evaluate using substitution. That's the cosine of 0 over 6, or 1/6. All right, and our last example from this lesson. Let f be the function defined by f of x equals e to the x cosine of x. Let g be a differentiable function such that g of pi over 2 equals 0. The graph of g prime is shown below. The derivative of the graph of g prime, that should be a comma there, oops. The derivative of g is shown below. Find the value of the limit as x approaches pi over 2 of f of x over g of x, or state that it does not exist. Justify your answer. So, first thing I try is substitution. I put pi over 2 into this. So I'm taking the limit as x goes to pi over 2 of f of x over g of x, which this is going to be, notice I'm not writing that this is equal. This is going to be e to the pi over 2 cosine of pi over 2 all over g of x at pi over 2, which is 0. Cosine of pi over 2 is also 0, so this ends up being 0 over 0, an indeterminate form. Use the arrow, not the equal sign, if you're going to write this. And then I apply LHospitals rule. This becomes the limit as x goes to pi over 2 of f prime of x over g prime of x, which is the limit of, as x goes to pi over 2, of negative sine of x e to the x plus e to the x cosine of x all over, and I get g prime from this graph right here, it's 2. I substitute pi over 2 in, and I end up with negative e to the pi over 2 plus 0 all over 2, and this ends up becoming negative e to the pi over 2 all over 2 as our limit. A little bit rushed at the end there. Hope you absorbed that in. I am totally out of time. Checking out with you. See you next time when we start Unit 5. Have a great rest of your day, everybody.